Okay, thanks everybody for joining us this time. We're very happy to have Daniel Carney, who's going to tell us about infrared quantum information. So Dan, please take it away.
Great, yeah, so thanks very much. I was really glad to get asked to talk about this specifically. This is based on some work I did with these people listed here about 2 and 3 years ago, and I haven't given a talk in maybe about a year. It was nice to revisit it. I think I have some different understanding of our own results. So this was done in collaboration with Gordon Semenoff, who's a professor at British Columbia, and then his students, Laurent Charette, who has left physics, and Dominic Neunfeld, who is a very smart German postdoc you should hire someday. He's in Perimeter Institute now. So the physics of this material is actually extraordinarily simple, I would say. And it gets a little technical in terms of the way you do the derivations. But I wanted to start by saying what's going on physically. So this is just a cartoon of an interferometer. So what I'm imagining here is that I have some source that produces, say, charged particles and shoots them down a beam, and then they hit a beam splitter, this operator U, and some mirrors. And basically what this beam splitter does is it takes the beam and it splits it into a superposition of a beam that's going in the same direction as it initially was, plus a state which has now, been moved 90 degrees and is moving on, say, the y-axis now. So this is just a naive description of what a beam splitter does in this equation here. And what the interferometry experiment does is it allows the superposition to propagate for some time, and it acts with the inverse of the beam splitter to recombine the state into something like the original state, or with some controlled phase between these two things. And then you just count how many things are coming out of the beam. And the key for this to work, the reason it's called an interferometer, is because the inverse beam splitter at the end, it's sensitive to the interference between the two terms, this x hat and y hat pieces of the superposition. So if you have a coherent superposition like I'm written here, then you can do the inverse beam splitter and get a coherent signal coming out. But on the other hand, if you don't, then you'll get a different answer. And so this talk is all about a source of this loss of contrast in an interferometer. So here I'm drawing a actually more realistic description of what happens in that experiment. So here I've got the same beam of charged particles getting shot down into a beam splitter. And now if you're careful and you think about what happens at the beam splitter, something that was neglected before was the fact that on the path that's reflected off of the mirror, the path that goes from the x direction to the y direction, that charge is accelerated. And since it's accelerated, it's going to Bremsstrahlung. So, these little wavy lines here mean Bremsstrahlung photons. They also mean Bremsstrahlung gravitons. I'll talk a little bit about it, but in the limits in this talk, these are basically the same physics, the gravitons and the photons. So what happens to the state is that now at the beam splitter, you have the initial beam comes back out with 50% probability, but then you get this complicated looking state here, which I've written py hat gamma h, which is this big entangled state containing the charge and also all of this radiation that flew out. And that radiation is entangled in a kind of obvious way. It knows which path you're on, or more specifically knows which outgoing momentum you've got. So if you then say, what happens, assuming you don't have some kind of perfect graviton detector, this radiation is lost. It's just the environment now. And so you should trace it when you make a prediction for what comes into the experiment at the end of the detector. And the statement here is just going to be, if you wait long enough, and then turns out to be a really long time, but in principle, if you want to wait long enough, that radiation is actually completely entangled with the hard charged particle. And so if you trace the radiation, you'll find a density matrix for the charge, which is just completely decohered. There's no longer any coherent superposition between the two arms of the beam. So basically, the rest of this talk is going to be discussing how you do this calculation, what it means in a lot more generality, and at the end, I'll talk a little bit about what this might mean about black hole physics. A lot of this was motivated by a proposal by Hawking, Perry, and Strominger on black hole physics. But I think if there's anything unclear at this example, we should stop and I can take questions.
Yeah, of course, this is a good time to remind people that if you have any questions, then please just unmute your mic and ask away. This is supposed to be interactive, so please use this opportunity.
All right, so sounds good. So, all right, so I'm going to do this entire talk. I know this is a relativity seminar, so I was a relativist by training, but this is all going to be formulated in terms of S matrices. So luckily, since it's a relativity seminar, I can use the S matrix conventions that I like, which is time runs up the paper, not to the right. Particle physicists hate it when I do this. So here's my S matrix. This is in total generality. Okay, so you have an incoming state alpha. Alpha and beta just mean lists of momenta and spins of the particles I'm throwing in. A time happens. There's this blob in the middle, which just means the sum over all the possible interactions. And then I get some superposition of states beta coming out. Beta, again, is some list of momenta and spins. And the amplitude, quantum mechanically, for some process alpha to beta is given by this S matrix element, S beta alpha, where S is just the time evolution from past infinity to future infinity. And that future infinity, past infinity is going to be taken quite literally in this talk. I really mean infinite time. That'll be important as we go. Okay. So the real technical workhorse in this work and sort of what started all of this was this sort of revitalization of what's called soft factorization theorems. These are very old results, but Andy Strominger started talking about them a lot, maybe 4 or 5 years ago. So I wanted to show you what they are. So they're very powerful tools for computing S matrix elements involving soft radiation. So basically the statement is, suppose I have some S matrix process, this diagram on the left, for an alpha to beta transition. And then I ask what changes when I include the emission of some soft photon or graviton. And the statement is that that diagram is equal to the diagram without the radiation times some simple factor, at least in the limit that the photon or graviton momentum k is going to 0. So that's what I mean by soft, right? It's just a very low energy photon flying away. So this is the statement of factorization. You just have a factor for the old S matrix and a factor for the soft thing. And this soft factor, there's one for photons and there's one for gravitons. They're given by these formulas, which I just wanted to put for completeness. What these are is you sum over all the legs of the diagram, all the hard particles, and then you put a factor for where you could have had the photon or graviton emitted, one for each leg, because you don't know which one it came out of. And then the key point is that there's this pole. So there's this 1 over p dot k in both cases. So p is the momentum of the charge or the massive thing off of which you're Bremsstrahlunging, and k is the momentum of the boson. So in the limit that k goes to 0, this is the leading order. It's a divergence. It's 1 over k divergence. But the real nice thing about this is you can repeat it. So if you have 2 photons emitted, you just get 2 of these factors. And if you have 3, you get 3 and so forth. And so what you can do is then use this to resum all diagrams with all numbers of photons or gravitons. So that's one way of deriving this thing called the infrared catastrophe, which is an ancient result in QED, at least. I think Weinberg, it was new with him in gravity. So the infrared catastrophe very schematically is the following equation. So if I take some S matrix element in total generality, and I add all of the loops of soft gauge bosons. So in other words, I add an arbitrary number of loops connecting the external legs, and I sum over all these diagrams. Then what you find is that S matrix element is the S matrix with none of these loops times this exponential, which has a pair of cutoffs in it. And what the cutoffs represent are sort of schematically shown in how I compute the loop here, right? So what I have in the loop is some propagator for the gauge boson, and I have to cut off that integral in momentum space. So there's a lower cutoff, little lambda, which is sort of like the photon mass. It just says you can't create an arbitrarily low energy photon. And the upper cutoff, big lambda, is sort of like an RG scale. It's just what we are going to call infrared physics. So anything below big lambda is infrared, anything above is not infrared. And you can adjust this in the final answers of the S matrix, as I'll show. So the thing we're actually interested in is this limit that the photon mass, this regulator, goes to 0. That is, it's unphysical to have it, and so you want to take it to 0 at the end of the computation. And the problem here is that in this formula, clearly this exponential, if you take little lambda to 0, the exponential just becomes 0. And so what you're saying then is that the S matrix is exactly equal to 0 for every process. So this is, a catastrophe in a clear sense. I mean, it would be bad if the S matrix was equal to 0. Nothing would ever happen, or so it was long ago known you had to solve this. And the classic solution basically goes back to Bloch and Nordzik in the late 30s. And then Jenny Frautschi-Sura did a non-perturbative version, and Weinberg added gravity to the mix in the 60s. But physically, it's pretty easy to know what it says. It just says, well, in drawing all those diagrams, you forgot, you're including all this virtual radiation, but what about the real radiation that actually flies out of the process and that you're not measuring? Okay. Much like that interferometer I was talking about. So mathematically, the way you do this is, what you do is you form an inclusive cross-section. So this sigma, where what I allow is now final states, which include radiation, up to some total energy E. And the idea is basically like, suppose I have a detector and it can only resolve photons above, a milli eV or something like that. Then what I'm going to do is I'm going to allow for, an arbitrary amount of photon radiation up to a milli eV of total energy, because I just wouldn't have seen it. And all processes emitting that or less are the same as far as I can tell in my detector. So mathematically, in this picture anyway, to make that cross-section, the cross-section is the amplitude squared, right? And so what I do is I take the amplitude, including all the loops and all the possible radiation states, and I square all those amplitudes up and sum it. And so using the soft factorization theorem, it's pretty straightforward to show that the answer, when you do this, is the original, the original amplitude squared, S mod squared, times 2 exponentials now. So one is the one I just showed you, the divergence from the loops, but now there's a new divergence, e to the negative little lambda over e, which comes from the radiation you just traced out, the radiation you just summed over in the final state. Okay, and the key point is that, one has a 1 over lambda and one has a lambda. And so if you multiply them, there's no lambda. Oh dear, I wrote this equation. Sorry, it should have, sorry, I wrote these notes a little late. Excuse me, they really should be in a pair of powers. The little lambda cancels out. And you're left with just a function, this f beta alpha lambda and e, which is just a function of the cutoffs, the physical things, the thing where you say what's the infrared big lambda and how much radiation you're going to get rid of in the final state e. And the point is just that this final answer is independent of little lambda. You can take it to 0, it's safe. So so what happened in this computation? So basically what you've done is you've taken, you wanted to compute the S matrix. You found that the S matrix is 0. And you found that to make a physical prediction, you actually have to forget about the S matrix and just look at the cross section. So you're only doing the probabilities, not the amplitudes. So now what we sort of asked ourselves was, what if you apply this directly to the state, to the amplitude? So if I try to apply it at the level of the amplitude directly. And so what you notice, if you do a little quantum information, is that the computation you just did was you did a trace over the soft degrees of freedom. So you have a Hilbert space factorization into the hard particles and the soft particles. And so I just write the soft particles as this little b here. And if you just write down what the sum over radiation s squared is in terms of bras and kets, it's obvious that what you're doing is tracing over this soft part of the Hilbert space. And so what that suggests is that one thing you can do is you can ask, what's the density matrix of the reduced density matrix of just the hard particles? So compute the state outgoing, trace over the soft particles, and ask what you get. And so that's an easy computation, which fortunately I wrote correctly now. So that's an easy computation. Again, just using the soft theorem workhorse, you just plug it through. And what you find, so this picture is showing what the density matrix is representing. It's saying I send in alpha, some fixed initial state that I prepare in my collider or whatever. And then I'm asking, what are the density matrix elements that contain a superposition of a pair of outgoing states beta and beta prime, right? So I'm asking basically, am I allowed to have superpositions of, a charge going to the left and a charge going to the right coming out of my collision? So you can write down the formula, including all of the soft stuff that's been traced out for this outgoing density matrix, and it's got this formula which looks like something with no radiation, two S matrix elements, one conjugated, just multiplying each other. Okay? One for the alpha to beta, one to the alpha to beta prime process. And then times a factor, little lambda to some power, where again, little lambda, we want to take it to 0. And the power are these sort of complicated formulas. So I wrote the one for the photons below. So this delta A is the sum over all of the lines and all the diagrams, times the charges on all of the lines, times some factor eta, which is +1 for outgoing states, -1 for incoming states, times some complicated function about which involves all the relative velocities between all the lines. And there's an even hairier looking one for the gravitational exponent, that's delta B. Main point being that the charges are replaced by M Planck inverse. So when you write this down, it doesn't look promising, like you're gonna get any good answers out of it. The one thing that is nice is these exponents are positive, or they're positive definite anyway. So you don't, okay, so what's the deal? So if the exponent is 0, that means that the density matrix element is gonna survive the lambda to 0 limit. If the exponent is positive and you send a little lambda to 0, it's gonna vanish. So the question is basically, what are the conditions for these exponents to be 0? So yeah, good. So this is just summarizing what I just said. So if I have an outgoing superposition to outgoing states beta, beta prime, I want to know if that superposition survives, if it's coherent or if it's decoherent by the radiation. That coefficient goes like this power of lambda, and it's gonna vanish unless these exponents are sorry, that should say vanishes if delta A, delta B are positive. So when does that happen? Yeah, I apologize. All of these greater than signs should be equals in this slide. So when are these exponents 0? When are they exactly 0? So a much nicer way to see what when this happens is the following set of conditions, which took us a while to find. So you can prove that those exponents are 0 if and only if a big set of currents are all identically equal. So this formula, there's a formula 1 for each gauge theory, E and M and GR. You know, the electromagnetic one is saying take all the particle species you have, that's I, take their charges, and then sum over. So take a vector V, a unit vector, and then ask basically how much charge in the state is going out of the celestial sphere at the angle V. So that's what this formula is saying. And my picture, I hope, is a little more clear. It's just counting charge coming out at a certain angle. The relativity version is the same. So this big EI of V is just counting how much energy is going out of the line. So that's just T naught naught at an angle. And the statement is, in terms of these currents, the key thing about these currents is that there's one for every angle. So this is a huge infinite set of currents. And the statement is that these exponents in the density matrix are going to be equal to 0. Again, sorry, they're equal to 0 if and only if all of these currents are exactly the same on the 2 outgoing states. So this is a very difficult thing to have happen, right? I have an S2 worth of constraints, 2 S2s worth of constraints, and I take 2 random states in the Hilbert space, and I say, unless these constraints are all exactly the same on both states, the superposition is going to be completely decoherent. So, you know, I think this looks a little abstract at this level, but it's actually very easy to see what this is saying. So basically what's going on is, what you're saying is, you know, here I'm drawing a simple process. I have like an electron scattering off a potential. So what happens? I have the electron comes in, it scatters off the potential, and it Bremsstrahlung some photon, or really a bunch of photons. Okay, and so now what I have is this entangled state of the charge on all these photons, this radiation gamma, I'm calling it. And the statement is just that the inner product between the radiation produced by a given process and another process. So you know, if the charge had come out at a different angle here, then the 2 radiation fields that those processes produce are orthogonal. They're exponentially close to 0 in the inner product. And the fact that they're 0, that mathematically it's easy to see. It's coming from this IR divergence, this 1/k pole in the emission in the S matrix. Physically, it's also very clear what you're saying is basically that the charge is moving around, it accelerates, and it basically just creates a long wavelength coherent state. It's actually just a classical electrical field, just the retarded potential, basically. And so the statement is, if I have a charge and it goes on one path versus a charge that's accelerated on another path, the 2 retarded potentials generated there are 2 classical configurations, and they're classically distinguishable. You can just tell where the charge was by looking at the radiation field it produced, which is in fact how you detect a charge. So I think physically it's not so crazy that you're getting this result. On the other hand, the interpretation of if this result is true, it sounds a little nuts if you think about it for a minute. So what it's saying is that the outgoing state, so say I'm at the LHC, I'm scattering stuff together, it's creating a spray, and I'm asking, are there any superpositions in that outgoing state? And the answer here is no. It's saying that, in fact, all of these off-diagonal elements are just 0. So on the diagonal, on the dense matrix, I have S matrix elements squared. So I get all the right probabilities. I get all the right cross sections. But there's no interference between these outgoing momentum states. And that seems very odd. You know, back to the interferometer I just showed at the very beginning, I mean, that would naively, if you took this seriously, what it would say is that if I do any interferometry with anything with a charge or a mass, that I cannot coherently recombine it because the state will have just decohered from all this Bremsstrahlung. And we know that's not true, right? You can do interferometry. It works very well. You know, the LIGO beams don't decohere from graviton Bremsstrahlunging. So so it makes you a bit nervous. It's like, did we do the computation wrong or what? I mean, this was just supposed to be some QED calculation. And okay, so, but it's true. I mean, the calculation's not wrong. So you might worry that but something about the way you've quantized the model is incorrect. So we can shelve that for a second, and now I want to revisit. There's a different way of looking at this problem. So it's usually credited to Faddeev and Kulish, although Chung and Kibble did it years before. Faddeev and Kulish have a really nice paper, though, and they deserve some credit. So the idea here is to actually change the problem. So before, what we were talking about is scattering, say, electrons. Like, I just prepare exactly an electron, I scatter it, and then it makes a bunch of photons. But so what these people all did was they said, well, maybe that's not what you really are doing in real life. Maybe what you're scattering is the charges with their fields somehow, with their Coulomb fields, say. And so they wrote down this formalism, which is called dress state, IR dress states. So I'll use this double bracket notation for a state alpha. This is the dressed state. So alpha is just a bunch of electron momenta or massive particle momenta in gravity. And then this double bracket alpha is now going to be dressed by the field. And so the dressing operator is given here. So what's important? Okay, one, it's an exponential operator. So you have to Taylor series and you get all these powers. The AK dagger creates the soft photon or graviton. And the factor in front of it is just the soft factor that we were using a long time ago for the emission. And there's an analogous formula for gravity. So the key is going to be basically what you've done is you're going to repackage all of that Bremsstrahlung into the asymptotic states. So instead of saying they're sort of disjointed, now the soft photon cloud, if you want, comes along for free with the charged particle. And there's some nice quantum information story about what these operators really are and so forth, but maybe I'll skip it for now. So I'm not going to prove this, but the way it's constructed is such that the S matrix elements in terms of these dress states are just finite. They're infrared finite because they just repackage the Bremsstrahlung into the state. So now you're asking, what's the amplitude for a dress state to go to some other dress state beta? And that question seems to be perfectly well posed at the level of the amplitude. Okay. So if you just take this forward and ask, what's the density matrix coming out? Well, you can write a perfectly nice coherent density matrix that looks much more like what you would have probably guessed it should look like. You know, you have these S matrix elements squared on the diagonal. That's the cross sections for the probabilities. But on the off diagonal, you have these coherent superpositions coming out, S1, S2 star and stuff in this matrix. And you might wonder, well, you know, what happened? But I hope it's clear. What happened is you just asked a different question. You said, now my outgoing states aren't just the charge superposed in two ways. It's the charge, but also with this cloud that comes along with it superposed. And the nice result is that this all works. You get a finite S matrix. You can make the density matrix. Fantastic. So there's been a long debate in the literature that, you know, maybe this is the right way to do things. That dressing states is correct and the inclusive formalism is wrong. But it was always kind of an annoying debate where you could calculate the exact same thing, the cross sections, they match in both formalisms, and then people just argue about which formalism is prettier. So here, what we're saying is something very concrete. You know, at the level of the cross sections, everything matches. So at a collider, who cares? However, when you actually really look at the quantum information of this, the inclusive formalism gives you what looks like a very wrong prediction, whereas the dress state formalism gives you what looks like the very much correct prediction, you know, in terms of I can do interferometry and things like that. So, you know, how strongly you want to interpret this is up to taste. You know, my take on this is that you have to be careful. I mean, you're really asking different questions. You're asking about superpositions of dressed or undressed states now. And the real question is, in nature, does this tell you what the states you're scattering are? So it seems to suggest that using these bare states with no dressing actually just doesn't make sense. It gives you the wrong physical predictions. So I box this in, in nature, do we scatter dressed or non-dressed states? You might say, case closed, I just proved it, we do the dress states. I personally would like to see an experiment done. So one thing you can do is you can ask, so I said at the beginning, I'm taking infinite time limits very seriously here. I'm really doing the S matrix, time from past infinity to future infinity. You can ask, how does this work with a finite time cutoff? And basically that finite time produces for you naturally an infrared regulator like the photon math. And you can go through these formulas and you can figure out what they look like with a large but finite time on your experiment. This statement being in a large but finite time, you can't produce a photon of wavelength bigger than the temporal box. And I think actually in electrodynamics and QED, you can potentially do an experiment where you could track this decoherence forming as a function of time in a long time in a beam splitter with a long baseline, for example. Unfortunately, in gravity, the exponent is so damn small because there's an M-Planck squared. It's just not, I don't think it's feasible. In fact, one of the reasons I personally got into this was I was hoping maybe there's an IR divergence and I can use this to actually detect the existence of the graviton. But I would say my conclusion there is it's not likely. Anyway, in principle, at least you could.
Sorry.
Sure, yeah.
Quick question. Can you hear me?
Yeah.
Okay. So just to check if I got it wrong, right or wrong. So you're saying that the difference between dress and inclusive formalism is like tracing out some additional environment in the form of the field associated with the particle, so that it acts as a decoherence, so that it brings your density matrix into diagonal form, into these pointer states, or that's wrong?
No, that's exactly right.
Okay.
And I mean, the really strong statement is that in this inclusive probability formalism, that's the only way you can get a finite answer out. you must do that trace. And so whether or not physically you should do that trace is kind of a tough question, because here's the rub. I mean, that trace includes two things. This radiation includes both actual physical Bremsstrahlung photons, which probably you should trace, but it also includes sort of like the Coulomb field of the charges, which you didn't include in the asymptotic state, right? You just took the undressed electron. And
yeah, sure.
So probably you shouldn't be tracing that, right?
Okay, thanks.
Yeah. Yeah, good. So I would like to see an experiment done, mostly because I'm thinking about experiments these days, but okay, this is the status of the stress state versus inclusive stuff. I want to say one more simple remark about another problem with the inclusive formalism, which is again solved by the dressing. So I won't go through this calculation. This is easy. You can see it in the introduction to one of our papers. Basically using all the same computations, you can now consider, instead of sending in a definite state alpha, which is some momentum, what if I send in a superposition? For example, a wave packet, like I actually send in. Okay, so here, just for simplicity, I'll do two discrete states, alpha, alpha prime. I superpose them, I shoot them in, I let them scatter, and I ask what comes out. And I hope by now, it's not too much of a stretch to imagine that what happens is, in this inclusive formalism where I trace out the soft radiation, the outgoing density matrix basically becomes a sum. There's a term for the alpha state coming in and scattering. Okay, that's this S alpha alpha S dagger. And then plus a term with the alpha prime state. And there's no cross terms. The cross terms are destroyed by the trace over the soft stuff. So what is this talking about? What it's saying is that you thought you superposed alpha and alpha prime, but actually what comes out is something where you just had a classical ensemble of alpha and alpha prime coming in. So in fact, the coherence of the entire scattering process is lost. It's all encoded in these soft photons. So that doesn't sound good either. I mean, you should be able to scatter a wave packet and have interference between terms in the wave packet, and this is going to destroy those. On the other hand, in the dress formalism, everything works like you'd think it would. So you superpose the dress states alpha alpha prime, and they just scatter perfectly well. I mean, why wouldn't they? You don't have to do a trace. You just use the dressed S matrix, and you get some nice coherent thing coming out. So this is just another thing that looks wrong in the inclusive formalism. Yeah, good. So I'm actually way under time, which is amazing since I was so late. So, so this is sort of all I think completely solid so far. So this is all just, I did a bunch of S matrix computations. They're the same in QED and gravity because we're talking about infrared physics. At the far IR, gravity doesn't couple to itself because it couples to energy, and the energy is zero here. You can calculate everything using theorems. It's great. However, why did we do this? Secretly, of course, we were interested in black holes. So let me do one slide of a little hand waving on black holes, which is a lot less solid. So Andy Strominger and then Malcolm Perry and Steve Hawking started talking about this idea, which was, okay, where's the black hole information lost? Well, I hope given the rest of this talk, it should be clear that the idea was going to be it's encoded in the soft stuff. Like, well, how do you formulate the black hole S matrix problem? You say I have a pure state, it comes in, and then it goes out in Hawking radiation, and oh my God, a pure state went to a thermal state. What happened? So how do I purify this thermal state? Where did that information go? Maybe it's lost, maybe not. So I think at the level of this talk, I hope it's very clear that in fact, and this I think is solid. I mean, if there is a black hole S matrix, it definitely includes soft corrections. There's no way of getting around that. And so here I'm drawing this sort of schematically. Here I have my state alpha, which comes in, it starts gravitating, forms a black hole, which is this little blob, and then eventually Hawking irradiates. And I'm drawing here this out state schematically. The idea here would be that it looks like some pure state, beta, which is the hard particles, which are the Hawking radiation. But then along with this is this soft stuff, B, the soft radiation, which is coming off of both the incoming lines and the outgoing lines. And even in just pure gravity, there's gravitons, it's going to happen. So I think it's clear actually that there is a lot of information encoded in this outgoing soft state. Great. Okay, so that's novel. I mean, that's an important point. I don't think anybody's ever taken the soft corrections to the Hawking radiation into account that I'm aware of. Does it solve the black hole information problem? Can you actually encode the whole initial pure state in this outgoing state of the Hawking particles plus the soft radiation? This I don't know, and maybe I'm skeptical that it could work. But let me give you some hints. Well, so A, it's not clear, I think, because of this dressed versus undressed stuff. Should you even really be thinking this way? Should you, is the information there? Should I trace it? I don't know. Still, there is a soft state. Okay, so it contains a lot of information. It knows what happened, roughly speaking. Numerically, though, is that enough to make up the black hole information, the black hole entropy? Can you actually compute it this way? And this we have tried and failed. So here's the closest sketch of how this could potentially work. So if you look at black hole formation in the iconal limit, meaning you're throwing together extremely high energy stuff at very small impact parameter, you think you should form a black hole, and this is a conjecture, and there's some evidence for this in string S matrix scattering, that the cross section for production of the black hole should scale like the area of the black hole. And so in this bottom line here, I'm writing S soft. So S soft means the entropy encoded in the soft stuff. So this is a not trivial calculation of doing the trace over the soft stuff and actually computing the entanglement entropy of the hard stuff. So it's true that in general, you can compute that as basically the cross section times some soft factor. Okay, so then what I'm using here is this conjecture that in the black hole production process, that cross section actually goes like the area of the black hole. And so you might say, well, look at that, I just derived an area formula. I have this entropy of the soft stuff goes like the area of the black hole times some factor. But the numerical coefficient, we don't know how to compute it. You'd have to know what the black hole matrix really is. Maybe it's a bit of a disappointment to say that we just don't know. It's certainly tempting to take this very seriously. But yeah, honestly, the statement at this level is there's information there. Is it enough? Just my gut reaction is probably I'm a little skeptical, but there's no proof that it isn't there. And who knows? Maybe we need a nice derivation. But I would say, the robust conclusion is if you want to do the black hole matrix problem correctly, you will have to include the soft stuff. There is information in there, and it would be really lovely to see that in some semi-controlled calculation of some type. So actually, that's all I really wanted to get through. So it's a bit short. I hope that's okay. But happy to take questions.
Okay. Thanks, Dan, for this very nice talk.
Yeah, this e-clapping is really the weirdest part of this.
Yeah, it's underwhelming. Okay, so great. We have time for questions.
Hi, I have a question.
Hey, Charles.
Hey, Dan. Or should I say, hey, Megan? Yeah, so when you talked about this idea of trying to actually measure this decoherence that you see in the inclusive formalism, I'm not quite clear exactly what that would entail, because how would you prepare an undressed electron or something to be able to do this type of experiment?
Yeah, I mean, exactly. So that's the question. It's basically when you prepare a state, are you preparing an undressed electron? I mean, so how do you prepare an electron? I mean, so imagine you're going to do the double slit, for example. I mean, you take a thing that boils electrons off, and you make a plate, and you put a little slit in the plate, and you let the electron just fly through it, right? And so it's already then hard to imagine how you're preparing a pure electron, because in fact, when the electron goes through, you Bremsstrahlung some junk. So probably the outcome of the experiment is it just proves to you that you'd had made the dress state in the first place.
But sorry, maybe I don't understand, but to me, an undressed electron would mean you have to have some configuration where you have a charge somewhere and no electric field, but that just breaks Gauss's law. So how could you possibly do that?
Yeah, exactly. I mean, so you can throw in some soft photons if you can organize that. So that's the way Andy constructs these states. So you can make it. So in the far infrared limit, you can't tell the difference between a virtual and a real photon. So you throw in the cloud. That's what the dressing does. Yeah. So indeed. So the experiment would be prepare an electron and shoot it through this thing. And the question is really, does the rate of decoherence match the rate of decoherence you would compute in either of these formalisms, right? So there's a rate you can compute in the inclusive formalism, and I think you're suggesting, and I would agree, that you're going to get the wrong answer. There's also a rate you can compute in the dress formalism, and you can check if you get the right answer. And that would just be a piece of evidence that this dressing operator is the correct thing and should really be applied to model nature. Does that make sense?
Yeah, I'm just not sure. I thought in the dress they didn't decohere.
It decoheres, but it's subleading order. So there's no 1/k pole, but there's a I forget what it's called. There's a subleading soft factor, which is like of order k to the 0, and so there is some rate. I mean, physically, it's been observed that you can have a photon Bremsstrahlung off of a beam splitter, and you'll see loss of coherence from that. So there is some rate. It's just the rate in the two formalisms, one is divergent and one is not.
Okay, great. Yeah, that makes sense. Thanks.
More questions? Matthias, you can just simply unmute your mic and ask directly. Oh, sorry. Oh, I see. So Matthias Folk asks, can you do the same for non-abelian gauge theory?
Oh yeah, that's a pretty cool question actually. So we're not probably okay. Not nailed down. So non-abelian gauge theory is obviously a lot hairier because you don't have true soft factorization, because a soft gauge boson can make a bunch more soft gauge bosons, and this so far is all abelian. So there is a dress state story by a group in, I think, Michigan, by Rabindranath Akuri, that seems to work pretty well for QCD. Gordon wrote a paper a month ago looking at some world line calculations in n=4 Yang mills, where you basically get the same sort of effect. So there's a sort of soft glue radiation, and you find that it decoheres the density matrix in basically the same way. That's a path integral computation, and like I said, it's an n=4 super Yang mills. So it would be nice to do just a standard Yang mills, a QCD computation in the S matrix formalism. The way to do it would be the KLN, to just repeat what I'm saying here, but just do it in the full KLN theorem, where you have to do the collinear divergences. My suspicion is this is all going to work the same way, basically. That if you look at the soft glue coming out, it's going to decohere the hard states. But it's not been proved. Sure.
Any more questions? Well, if not, then let's thank Dan again for this very nice talk.
Yeah, thanks, guys.
Oh, I think somebody actually wants to ask something.
Oh, okay.
Whoever it was, maybe you can just ask away. No? Okay. Well, anyway.